All right, so the next topic we're going to take a look at is the counting principle. This is going to lead us into combinations and permutations and probability. The probability of an event happening, the percentage that something will or will not occur. Starts with the counting principle. The counting principle helps us determine how many ways something can happen. With the counting principle, we look at multiple different events. And what we do is we look at how many ways a certain thing could happen. And the number of ways that could happen, we call that, we could label it E1. And so if I take the number of ways that one thing can happen, and then the number of ways that a second event could happen, and the number of ways that a third event could happen, if I want to know the number of ways that all three things would occur, I can simply take E1 times E2 times E3. The counting principle just simply allows us to multiply the number of ways that one event can happen, and that will tell us the number of ways that an entire thing can occur. I know it sounds confusing, but let's take a look at an example first. Poof. So like magic, we have a problem. You own 12 shirts, 4 pants, and 6 pairs of shoes. How many different outfits can you wear? So the counting principle simply says that how many ways we can do each individual event multiplied together will be the number of ways that we can do the entire event. So we start with shirts. I have 12 different shirts that I can wear, so there's our event 1, 12 different possibilities. We have 4 pants that we could wear with those shirts, and so that's a different event. So I'm going to multiply that by 4. That would tell us how many shirt-pant combinations we have. If I multiply those together, that's 48. So I have 48 different shirt-pant combinations. Then we throw in the shoes. I have 6 pairs of shoes that I can wear. Now we're going to assume that you're wearing the same right shoe as the left shoe, right? That would change things just a little bit, but let's say when you wear a pair of shoes, you wear the same shoe right and left foot, and so I have 6 different ways that I could wear those shoes. And so if I multiply all of that out together, 12 times 4 times 6 is 288. So with 12 shirts, 4 pants, and 6 shoes, I can wear 288 distinct, different outfits. So when you look through your closet and go, I have nothing to wear, yeah, you do. You have a lot of different combinations you could wear. Now, that's assuming those all go together. That deals with fashion and all those other things, but mathematically, 288 different possibilities. Okay, so let's take a look at one more example of the counting principle. Gotham City license plates, Gotham City, home of Batman, start with 3 letters followed by 4 numbers. How many unique license plates can be created? And we're going to alter this question after we go through it. So first, we have 7 different positions, right? So each position we can think of as an event. So in the first position, it's got to be a letter. Any letter will do. So for that first position, there are 26 different letters that we could choose from. For the next event, we need another letter. It doesn't say anything about being able or not being able to repeat letters, and so we have 26 more letters to choose from for that second position, and 26 more letters to choose from that third position. Next, the last 4 entries on our license plate need to be numbers. There's no restriction on those numbers, and so that first number could be any number, any single digit. It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's 10 distinct numbers that we could have on our first number, and then the same thing for each subsequent number. We have 10 possibilities for each one of those as well. And so, with our 7 different positions, 1, 2, 3, 4, 5, 6, 7, we have all of those different possibilities, and all we need to do is multiply all those numbers together. And so we just grab our calculator, multiply that all out, and we get 1,757,600,000, 175,760,000 different license plates we can have in Gotham City, where we start with 3 letters and then end with 4 digits. So that's a lot of people that can get a license plate that's unique, all right? In the United States, we often change that. Trucks can have 2 letters and then 5 different numbers instead of this setup, and so you can create even more. And so that's how we can have the entire United States have different license plates for their vehicles, because just in this setup alone, we have 175 million, almost 176 million different combinations. That's a lot of license plates, right? And so we can keep on creating and generating more and more license plates without fearing that we're going to have to repeat. Now, What if there were restrictions? Let's change up the problem just a little bit. So let me get rid of these numbers, and we're going to keep this same setup, except I'm going to add two little details. So poof, what if I decide to throw in no letter or number could be repeated? So that changes things up just a little bit. Our first entry on our license plate has 26 different letters to choose from. Our next number that we could, our next number that we could put in, our next letter that we could put in, we don't have 26 possibilities anymore. We have locked in a letter here. Who cares what letter that is? A, B, C, D? Whatever letter that is, I can't use it again, so that only leaves me with 25 different possible letters to choose from. Once I've chosen that letter, whatever that letter is, my third letter again can't be repeated, so now I only have 24 letters left to choose from. When I go to the numbers, that first number, I have all 10 digits to choose from, 0 through 9, and so I have 10 possibilities for that number. However, the next number, I've already chosen a number in that first position. I can't repeat that number, so that only leaves me with 9 possibilities left, regardless of whatever that number is in that first numbered position. The next number after that, I've already used 2 numbers, so I only have 8 possible numbers left to choose from, and that last number, I only have 7 different possible numbers to choose from. And so notice how this is different than our last example. Our last example was 26, 26, 26, 10, 10, 10, 10. Now we just have different numbers. If we multiply all of those together, we still have quite a few combinations. We still have 78,624,000 combinations, different license plates that we could create. Now this is way smaller than the other number. 175 million is what we had before. So we lose almost 100 million license plates simply by saying a letter and a number can't be repeated. So that can drastically change and alter a problem depending on the rules and the stipulations for the counting principle. So the counting principle leads us to another idea, and that idea is called permutations. So with permutations, it's basically the same thing. What a permutation is, a permutation of so many different elements, of n different elements, is the ordering, such that one element is first, and then another element is second, and then another element is third, etc., etc., etc. Very similar to what we just did, permutations and the counting principle go very much hand in hand. So we can take a look at this example that is about to appear on our screen. And poof, like magic, how many permutations of A, B, C, D, E, F are possible? This is the counting principle. That's all that this is. And so if we were to place these letters in a certain order, when we choose that first position, there are 6 different letters that we could put in that first position. The next position, once we've chosen that letter, we can't possibly choose it again because we're looking at how many ways we can order these 6 things. So once I've chosen a letter, the next letter, there's only 5 letters left for me to choose from. The next entry, there's only 4 letters, and then the next 3, and then finally 2, and then 1. There'll be only 1 letter left for me to put in that last position. If we multiply that all out, that tells us that there are 720 different permutations, which is what the counting principle is, 720 different permutations for the letters A, B, C, D, E, F. Imagine if your homework was to list every single combination. You don't want to do that. This leads us to an idea in mathematics. When we look at not the answer, but how we created the answer, the 6 times 5 times 4 times 3 times 2 times 1, we can actually write it like this in math. We can write it as 6 with an exclamation point. Now, that doesn't mean we're all excited about 6. 6! That's not what that is. We state this as 6 factorial. That's what the exclamation point means in mathematics. It means a factorial. And what a factorial is when we see 6 factorial, it simply means you start with the number 6, and then you multiply by the next integer below it, 5, and then the next integer below it, 4, 3, 2, 1, and that's it. You always stop at 1. You don't want to go to 0 because then the product would be 0, and every permutation would be 0, and that's not right. So if I had, say, 10 factorial, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? So that's the idea of a factorial. This leads us to a theorem that we have in math that will appear in our lower left corner. And like magic, there it is. The number of permutations of n elements is n factorial, which again, n factorial means n times n minus 1, 1 less than n, times n minus 2, etc., etc., etc. We keep doing that, times yada, 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 until it's times 2, and then times 1. All right, that's what it means to be a factorial, and that's how we get the number of permutations. On our next video, we will look at more permutations, we will look at distinguishable permutations, and then we'll also look at combinations, and at the end of that video, I will give you some more practice that will practice all of these concepts, counting principle, these permutations, and the combinations that we're going to get to. So until the next video, have yourself a great day. Stay safe out there.